We're now going to learn all about logarithmic differentiation and walk through some examples. Logarithmic differentiation is used for differentiating products and/or quotients with many factors, or complicated expressions where both the base and the exponent are functions of x. Down here, I wrote down examples of each of these. The first function is an example of a function that's made up of a product and a quotient and is pretty complicated. And then the second example is an example of a function where both the base and the exponent are functions of x. I wrote down 4 steps that we can follow when we use logarithmic differentiation. The first step is we're going to take the natural log of both sides of the equation. The second step is we are going to use what's called laws of logarithms to simplify the right-hand side. I listed these 3 laws right down here in this green box to make things easier. Step 3 is we are going to differentiate both sides of the equation with respect to x. And then step 4 is we're just going to solve for dy dx. And here's the important part. We have to remember at the very end to substitute the original expression for y into our solution. Let's now walk through 2 examples where we are going to use logarithmic differentiation to find the derivative of the given function. The first function that we're given is y is equal to x times x squared plus 1, all divided by the square root of x plus 1. Our first step is to take the natural log of both sides of the equation. So we have ln y on the left, and on the right we have ln of x times x squared plus 1, all divided by the square root of x plus 1. Our second step is to work on the right-hand side and simplify that using the laws of logarithms. So our left-hand side stays the same, ln y. The laws of logarithms are going to help us break up our right-hand side. So we're going to write this as ln x plus ln x squared plus 1. You use a plus whenever things are multiplied. And then when things are divided, you use a minus. So we have minus ln of the square root of x plus 1. I'm just going to remind us here that the square root of x plus 1 is x plus 1 to the 1/2. So we can do one more step of simplification, and we're going to pull that 1/2 out in front. So this becomes ln x plus ln x squared plus 1 minus 1/2 ln x plus 1. Now we're ready for step 3. Step 3 tells us to take the derivative of both sides of the equation because we want to find dy dx. So we have the derivative with respect to x of ln y on the left, and on the right we have the derivative with respect to x of ln x plus ln x squared plus 1 minus 1/2 ln x plus 1. The derivative of ln y is going to be the derivative of what's inside, so that's dy dx, all divided by what's inside, which is y. And on the right-hand side, we're going to have 1 over x plus the derivative of ln x squared plus 1, which is the derivative of what's inside, which is 2x, all divided by what's inside, x squared plus 1, minus 1/2 times the derivative of the natural log of x plus 1, and that's just the derivative of x plus 1 on the top, which is 1, and then our x plus 1 in the denominator. I'm going to go ahead and copy this, and we'll take this with us to the next page. Now we're at step 4, where we are going to solve for dy dx. So we're going to take the y that's sitting in the denominator and take it to the right-hand side. So we have dy dx is equal to y times 1 over x plus 2x, all divided by x squared plus 1 minus 1 over 2 times x plus 1. Now the last thing we have to do is substitute back in what y is. So we have to go all the way back to our original function and plug that in. So we have dy dx is y, which was x times x squared plus 1, all divided by the square root of x plus 1, times what we just had, 1 over x plus 2x over x squared plus 1 minus 1, all divided by 2 times x plus 1. And it's long, but that is our final answer. Let's now look at our second example. This is an example where we have a function raised to a function. And the only way to take the derivative is to pull that function out of the exponent by using logarithms. Let's start with step 1. Step 1 tells us to take the natural log of both sides. So we have ln y is equal to ln of x sine x. Step 2 is to simplify our right-hand side. So we have ln y is equal to sine x times ln x. Whenever you have an exponent, you can just bring it right out in front. Step 3 is to take the derivative of both sides. So we have d dx of ln y is equal to d dx of sine x times ln x. The derivative of ln y is the derivative of what's inside, which is dy dx, all divided by what's inside, which is y. And then on our right-hand side, we have a product. Here's our first function, and here's our second function. So we're going to use the product rule. So we're going to have the first, which is sine x, times the derivative of our second function. The derivative of ln x is 1 over x, plus our second function, ln x, times the derivative of our first. The derivative of sine x is cosine x. Now for our fourth step, we just have to solve for dy dx. So we have dy dx is equal to y times sine x over x plus ln x times cosine x. And then our last step, which is easy to forget, is to go ahead and substitute back in what y is. Y was x sine x. And then we multiply this by sine x over x plus ln x times cosine x. And that's our final answer. And that's it.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.